Good evening, everybody, and welcome to another IDEA community webinar during this COVID-19 season. Thank you for everybody who's joining us live, and thank you for those who are watching this video later on, perhaps through the IDEA website. Tonight, we're welcoming Andrew Yale, Dr. Andrew Yale, who recently defended this work as his PhD dissertation, and he can explain more about that. Just a couple logistics. I think it works best if we hang on to our questions, our verbal questions, until the end or such time that Andrew or I invite the questions. Feel free to jot down questions so we don't forget them in the WebEx chat. And we are recording it, just keep that in mind. And for those of you who are watching this who are Tetherless World graduate students, please sign up for the end of term Tetherless World lightning talks. Check your email, you know how to sign up. So without further ado, I'm going to hand the ball back to Andrew here. I think I just slide it over to him. And Andrew, you're in charge.
Okay, thank you. Yeah, so let me know if there's anything that pops up in the chat, because I can't, I won't be able to see that presenting here. But yeah, so my name is Andrew Yale, and yeah, so I just defended my dissertation on this topic, but I'm going to speak to you about privacy-preserving synthetic health data generation and evaluation. Oh, I think I'm getting some echo. Okay, cool. Okay, so just an outline of this talk. So first, we're going to talk about the synthetic health data problem. Then we're going to talk about our HealthGAN for synthetic data generation. Then we're going to talk about evaluating the synthetic data. Then we're going to talk about applying this to an Optum Lab synthetic data generation problem. And finally, conclusions and future work. So the synthetic health data problem. So why are we focused on synthetic health data? So electronic healthcare records, or EHR, are captured for almost all patients in the US, but EHR is necessary for this health informatics and education and research as well, but privacy concerns prevent distribution. Laws like HIPAA and GDPR, and this is for good reason. We don't want to expose this medical information. Freely available resources such as Mimic or Cynthia don't really solve this problem. They don't really reflect a diversity of problems or are slightly different from what you would really want in a education or research setting. And most current synthetic data generation methods don't really handle categorical, mixed categorical and discrete data very well. And then finally, we want attempts for healthcare data are not really suitable for education or research. So what are we proposing as a solution? So we're proposing that an end-to-end workflow. And so first we'll gather data, so create a cohort of real data, run an analysis on that, normalize the real data, and then train a model that can generate synthetic data, measure all of the privacy, resemblance, and utility in a secure environment, and then export the model outside of the secure environment. And so this kind of creates a couple of different factors of how we want to accomplish this goal that we'll go through. So yeah, so again, we want to create this end-to-end pipeline. So we need to define the properties of synthetic data. We're going to develop a generative adversarial network approach for mixed categorical and continuous data. We're going to develop metrics of success for the synthetic data. We're going to create a test bed in Mimic first with multiple different studies. Then we're going to perform a benchmark study of these different competing synthetic methods on the Mimic data. Test the utility of the synthetic Mimic data on these studies for classroom and research settings. And basically, that's kind of the preparing all of the generation and evaluation methods. And then we're going to take these finalized methods into the Optum Lab secure environment and use real data to develop a suite of, to replicate 2 different studies in the secure environment and export the models outside of the secure environment. So defining metrics of success. So we have 5 different properties of synthetic data that we want to focus on: privacy, resemblance, utility, efficiency, and approach. So we'll go through those one by one. So first, privacy. This is the most important, especially when we're talking about real medical data and laws such as HIPAA and GDPR. We want to, first and foremost, we want to protect the privacy of the patients. So there are certain theoretical guarantees for algorithms, such as differential privacy, but for our research, we're focusing on the empirical evaluation of privacy. So we want to, and there's kind of 2 aspects of that. There's the synthetic data evaluation. Is the synthetic data too close to the real data? Are we exposing privacy in the synthetic data? But also, since we're exporting a model, we need to evaluate that model. Does the model contain or require real data to generate samples? Since that's going to be potentially public as well. So for the Optum Labs, we specifically want to empirically evaluate the synthetic data and the model for unrestricted use created from de-identified data. Next, resemblance. So if once we can guarantee or measure privacy, we need to also be able to measure the resemblance to ensure that we are preserving resemblance as well. So there's kind of 3 different facets of that. Distribution resemblance. How well does the synthetic data maintain statistical similarities with the real data? How well, does the synthetic data preserve univariate and multivariate distributions? Coverage resemblance. Is the support of the real data the same as the support of the synthetic data? Are the generated samples within the support of the real data? And finally, fidelity resemblance. And so that has to do with whether the generator can preserve qualitative features. So for instance, if age is in the real data as a discrete value, a lot of methods that are generating synthetic data will then bin the age into like 10 to 20, 20 to 30, et cetera, just to make sure that privacy is preserved. But you lose a lot of resemblance in that because it's almost like a different feature at that point. So we want to be able to preserve the qualitative features. So one of the methods we use to measure this were PCA plots. So you can kind of see that over on the right. And you can see, so the top is the original data, or the real data, and the bottom is the multivariate Gaussian method. And so we can see that the multivariate Gaussian is generating data that looks very similar to the original data, but I don't know if you'll be able to see my mouse, but basically in the lower left of this, it kind of spreads out beyond this sharp end we see in the original data. So we can see, I mean, it's a multivariate Gaussian, so we can see almost this Gaussian shape to it, which is not exactly within the support of the original data. Next, we want to look at utility. So once we can measure privacy and resemblance, and we're getting good values for that, we want to be able to measure the utility of the data to ensure that we can use it for education and potentially research. So we're going to look at targeted versus universal utility is what we're defining. So targeted utility is defined as using the synthetic data for planned tasks. So specifically, you have one data set that you are, accomplishes this task on the real data, and you want to basically replicate that on the synthetic data. And so that's what we'll be focusing on. Universal utility would basically be if you had any arbitrary amount of data and types of data, and then it tried to accomplish a task on the synthetic data that you don't necessarily know when you're generating the data. This is a lot more difficult to test as well as accomplish, so we're not going to focus on that for this work. Next is efficiency. So we want to look at computational training efficiency. How long does it take to train a model? So as we'll kind of discuss, we're working with neural networks. So those are inherently pretty long to train, but it is just a matter of if you have GPUs or something like that, you can speed up the whole process relatively quickly. But well, I'll get to that later. So size efficiency. Does the model store the real data points? So this is a problem since we need to export the model. We can't have the model be on the scale of the original data because it kind of shows that there could be some exposure of original data in the model itself. Generation efficiency, how quickly can the data be generated once you've trained the model, which with neural networks is pretty quick. And then finally, modeling efficiency, how much human effort does it take to set up a new data set? So this is kind of a big trade-off, the modeling efficiency between the modeling and the computational training efficiency. So neural networks definitely take longer for computational training efficiency, but so Synthia is another synthetic data method, and basically what they did was they create synthetic data using these kind of flowcharts. And so basically these are based off of population level statistics, and so they kind of have to handcraft these for each new data set that they want to make. So there's a lot more modeling time going into it because you have to create a new flowchart based off of population level statistics and ensure that those statistics are accurate, versus the model we're looking at, while training slower, doesn't require as much human input. The human, can just take the data and kind of throw it into the GAN and train the model. And finally, approach. So there are a couple aspects of this as well. So source distribution, are we only using real data to train the model, or are we using a combination of real and modeled data to augment the model? So this might be used for a classroom setting where we want to change the result of the synthetic data to ensure a certain relationship exists. Or are we using completely new data that doesn't exist to train the model? We're only going to be focusing on real data for our purposes. The format of the data, longitudinal, tabular, or derived features. So we're going to be looking at tabular data with derived features rather than longitudinal. While longitudinal is the goal, especially with something like electronic health records, which are inherently time series data, it's definitely a more difficult problem, and we're actively working on improving our methods to work on that, to work for longitudinal data, but I'm not going to be presenting about that today, really. And then generation method, how is the data going to be modeled? Are we looking at like an exemplar-based model, a kernel-based model, or neural networks? And like I said before, we're going to be focusing on a neural network as our final model. So the HealthGAN for synthetic data generation. So what is our model? What are we actually going to be doing? So basically, we wanted to look at a bunch of different models and kind of look at why certain models would be good for certain reasons and bad for certain reasons, and be able to compare them against our final model, the HealthGAN. So I will go through those. So we have the multivariate Gaussian, the Parsing windows, additive noise model, which is another model that we created that's based off of random forest. Differential privacy obfuscation, so not a full differential privacy synthetic data method, but a obfuscation method that basically attempts to remove the identifiers using differential privacy from the data. Copying the data, which is basically just a benchmark to compare against, obviously not private at all, and the HealthGAN. So again, kind of looking at these and what they're good at and what they do poorly at. So for instance, obviously, so copying the data, for instance, has very poor privacy, but is very good in terms of resemblance and utility because it is the original data. Whereas the differential privacy obfuscation has good privacy because it removes the quasi-identifiers, but has some loss of fidelity because you are doing things like binning the ages and stuff to ensure differential privacy. And so we're going to compare all these methods. So to kind of take a step back here, I've been talking about the HealthGAN, but what is a GAN to begin with? So a generative adversarial network, or a GAN, is a neural network model for generating synthetic data. So basically, there are in the setup, there are two different neural networks, G and D here, the generator and the discriminator. And so basically, what you're doing is you're creating a generator network that will take samples from a latent space, basically noise, and generate synthetic data. And so then those synthetic data and real data will be fed into the discriminator. And the discriminator is basically trying to determine it's trying to learn what is real versus what is synthetic. And so basically, these two neural networks are working against each other. The discriminator is trying to be able to tell the difference between real and synthetic data, and the generator is trying to fool the discriminator. So the idea there is that as you train, you get a better generation of synthetic data, but you also get a nice like min-max where since they're in equilibrium, I should say, between the two, where there's not going to be as much of a risk of overfitting because the discriminator should be able to kind of combat the overfitting of the generator. So this has already been attempted for medical data. So the medGAN was a GAN used to generate medical data using mimic data, which is also what we wanted to do. And they added a couple things to the baseline GAN formulation, but for all intents and purposes, it was pretty much just a GAN designed to work on medical data. But it was limited to binary and count data. So this is another thing, I guess, taking a step back, is that GANs were originally designed for images. The nice thing about images is that every single value is predictable in terms of being between like 0 and 255 or something like that, depending on the image. But basically, it's a predictable pixel values. And so they limited to binary and count data to try and maintain that predictability. And so we first looked at this, but we were realizing that it had poor fidelity. It was only using these binary or count data, and specifically what that binary and count data was diagnosis codes. So basically, if you think of a matrix, each row is a patient and each column was a diagnosis code, and the cell was either binary, in the binary version, whether they got that diagnosis or not, and in the count version, the number of diagnosis they had of that diagnosis code. And so what they were really striving towards was achieving a good dimension-wise probability, which was basically column sparsity. They wanted, across a population of people, are we seeing a very similar number of, or a percentage of patients with these specific diagnoses? And so they were achieving that. I mean, we can see here, so this is the original data, and so each dot is a column, and the synthetic data here, and you're trying to basically be on this line here, where in the original data, 40% of the patients had this diagnosis, and in the synthetic data, you also get around 40% having that diagnosis. Now, while this matched, the issue was if you looked in the other dimension, you were looking at basically the row sums, and so the row sums can be interpreted as the total number of diagnoses per patient. And so when we look at that, the original data in black here, we can see that there were no a real patient with over 100 diagnoses, but in the synthetic data, we get up to almost 500 on one patient. Excuse me. So obviously they were kind of basically overfitting to this, to achieve this goal while this goal was slipping. So that was kind of an issue as well. So we kind of looked past the medGAN, that kind of took the ideas from that and looked at the Wasserstein GAN, so the WGAN. So this is basically a different modified version of the original GAN architecture. Basically what it's changing is, in the normal GAN architecture, a discriminator is trying to give a percentage value, a probability, to whether it thinks the data is real or fake. In the Wasserstein GAN, it's giving a distance it thinks that the data is from the real data. So the idea being, in a normal GAN, when the data is arbitrarily far away from, the synthetic data is arbitrarily far away from the real data, you can have an issue where your gradients don't really make sense. You have like infinite gradients because it always knows that the data, which is real and which is fake. Whereas in the Wasserstein GAN, that's a continuous value. As the data gets farther away from the real data, you always can decrease that value and get closer to the real data. So it basically is just a more stable version of the original GAN. Another issue, as kind of alluded to before, is that we kind of need the data to be predictable. So in the original GAN formulation, this was for images, so it was very predictable what the values would be. And in the medGAN formulation, it was, in binary at least, it was 0 or it was 1. It was also predictable. So if we wanted to work with continuous, discrete, categorical, and binary data, we needed to be able to make that into, change that into a predictable format. And so what we did was we, for the continuous values, we just standardized it to be between 0 and 1. But for discrete, categorical, and binary data, we used the encoding from the Synthetic Data Vault paper, which basically maps things like categorical data to 0 to 1. And so we can see an example right here where if you have yes showing up in your data 40% of the time, no 50% of the time, and maybe 10% of the time, then we can map it based on sorting on the most likely to be no, yes, maybe, and then draw from truncated Gaussians to create these values between 0 and 1. As we went through and that was basically our original formulation, our phase 1 formulation. And as we went through and tried this on different data sets, as well as moved up to more complex data sets, we needed to kind of make some improvements to the HealthGAN formulation. So we also introduced ordinal mapping. So I'll skip down to this one for now. And so basically what we were just talking about with the SDB encoding, problem is that if you look at this, it says no, yes, maybe. So when you sample from over here and maybe the synthetic data gets generated over here and you get kind of a sample that goes from no to yes, that doesn't really make much sense because ordinally speaking, it should be no, maybe, yes. You have kind of an order there. So what we did was for ordinal variables, rather than sorting by most popular, our most frequent, we sorted by the ordinal value. And so this increased our ability to generate synthetic ordinal data. So now that we have a method for generating the data, how do we evaluate this synthetic data? So first we created a kind of testbed data set to evaluate all of our methods and create metrics on. And so what this did was it was a data set that had basically many different types of data. It was from the MIMIC data set, which is ICU data. So we were basically trying to get ICU data on patients to predict 48-hour mortality. So we had vital signs such as heart rate and temperature, which are continuous and span different ranges, which is why we needed to standardize, as well as we had demographic variables such as ethnicity, marital status, and these were categorical so that we could test out our categorical mapping. We also had diagnosis codes. And so we actually, the issue with diagnosis codes is that they're very sparse. We saw this in the medGAN data as well, where there was only one diagnosis code that was even close to 40% of the existing 40% of the time, which makes sense. There's a lot of people that go through the ICU and a lot of different conditions that they might have in ICD codes. So we used the clinical classification software to basically bin these diagnosis codes, and so take it down from, I think, around 1,000 or so diagnosis codes that were existing in the data set to 281. And so between that, we got 26,000 or almost 27,000 observations and 339 different features that we were testing all our methods on. So in terms of quality metrics, we went through a couple different metrics. So we have the visual assessment with the PCA plots, which I had shown you earlier, and we'll go through those again. And then we have a novel metric, the nearest neighbor adversarial accuracy. And then we also test with the membership inference attacks, discriminator testing, and utility testing. So visually assessing resemblance using a PCA. So again, in the black over here is the original data. And all these plots have both plotted with the red being synthetic. And so we can see with that multivariate Gaussian, you kind of miss this upper right and you kind of extend too far on this lower left. The additive noise model, which was the random forest based model, fits the data pretty well. The differential privacy, you can actually see almost where the quasi identifiers get cut off in this upper left. The pars and windows looks relatively similar to the multivariate Gaussian with a little bit extending too far. And then the HealthGAN looks very similar to the additive noise and similar, ideally, to the original data. So I mean, this is fine, but this is not. This is more qualitative, not quantitative. So how do we quantitatively measure this? And so we developed the idea of nearest neighbor adversarial accuracy. So to set this up, think of T, a target distribution of real data, and S, a source distribution of synthetic data. And then so this is a nearest neighbor method. So what we're going to do is measure DTS of I as the the distance between a point I in T to its nearest neighbor J in S. So basically the point so take point I in your real data, what's the distance to its nearest neighbor in the synthetic data. And then we'll also have DTT, which is basically within the real data from point I, what's the distance to its closest neighbor in the real data that's not itself. And so the idea is we can, with DTS, DTT, as well as DST and DSS, we can create this balanced accuracy type metric where it's basically looking at whether it's comparing whether from any point I, whether your closest neighbor is within your own data set or outside of your own data set in the synthetic data. And so the idea is that if you're achieving a high level of privacy and resemblance, you should be getting around a 0.5 in this balanced accuracy type metric. If they're indistinguishable, yeah. And so we can measure this with the training data, with the testing data, and with across our synthetic data sets. And so to kind of show this graphically, if we look over here to the left, with the blue data being the real data and the red data being your synthetic data, in this version right here where you have a terrible model, it's creating synthetic data that doesn't look at all like the real data. We have our training adversarial accuracy as 0.77 and our test as 0.78, which are not near 0.5, which is what we were talking about. I guess I also didn't explain. So we also have the privacy loss. So basically your privacy loss is going to be the difference between your test and your train adversarial accuracy. And so, since the privacy loss, you want that to be as close to 0 as possible. So basically, and this makes sense, this is saying that we have good privacy loss, but that's because our data is so bad. So we have good privacy because our model is generating poor synthetic data. In this next kind of well-fit model, we see that the data looks like the real data, but it's not exactly like the real data. We're getting a 0.49 here, we're getting a 0.51 here, and we're getting a low privacy loss. So again, that's the model we want in terms of having a good level of resemblance near 0.5 for both, as well as low privacy loss. And then over here, where we basically have almost the exact like an overfit model, almost exactly the training data, we get a training adversarial accuracy of 0.0, which is showing that we're overfitting too much. 0.52 on the test adversarial accuracy, which makes sense because the test and the train should have a good fit. They should be indistinguishable. So our privacy loss is poor. And so again, kind of like looking at over time as you fit your model, if you go from this is our left model that was poor, we have a good privacy, but our resemblance is poor. As we get to kind of like our ideal point here where we're fitting properly, we have 0.5 for both, and we have low privacy loss. But then as you overfit, you start to lose your privacy as well as overfit to the data. Another metric we're using is the membership inference attack. And so this is, a lot of times this scenario is used when you have data and you're trying to figure out whether the data was used to train a model. So this is like a slightly different scenario because we don't, so we want to consider an attacker with access to some of the real data and some of our synthetic data. And basically, we want to see if the attacker can use the synthetic data to identify the real data. Basically, if it can determine which was real and which was synthetic. Or sorry, not which was real and which was synthetic. Whether it can use the synthetic data to identify the training versus the testing is basically what we're using, because we have two sets of real data, and if somebody can figure out whether they use which the training data is and which the testing data is, then we're overfitting to the training data, basically. And this is measured using area under the curve as a classifier. And so basically what we can see here is that on the left here, this is using the this is using a copy of the data. So basically the idea, so if you use the training data as your quote unquote synthetic data, you could easily differentiate between the training and the testing data. That makes sense. You know, if you have the actual training data, you should be able to determine the difference. With the HealthGAN generated synthetic data, we're getting we're not able to tell the difference. So you can see right here, plotting the what the distances, we can see that there's no distinguishable difference between the training and the testing data. And then finally, in terms of privacy and resemblance, we're looking at discriminator testing. And so the HealthGAN has that discriminator that I was talking about, which measures the distance between the data that's passed in and what it thinks the real data looks like. And so we can feed data into the discriminator, and it will basically give us back this distance, so we can tell if we can try to measure whether we're overfitting the data. Because if we look here, when you feed in the real data that was used as training data, you get a distance of negative 0.013. Very close. That makes sense because the discriminator has been using this data. When you feed in the testing data, you get negative 0.065. So even the testing data, which is from the same distribution as the training data, has a slightly larger distance. So basically, if your distance is less than the testing, you know that you're overfitting to the training data because not even the testing is that close to the training data. Finally, we have utility testing. So this is kind of different per data set. Again, I said that this benchmark data set that we're using is a mortality data set where we're trying to measure 48-hour mortality in the ICU. So for this one, we're just going to use that measure using logistic regression. We're going to try to predict 48-hour mortality in the ICU on synthetic data. But this could change from data set to data set. So to kind of share those results, we can see over here. So I'll actually start over on the right. So with a copy of the data, our training adversarial accuracy is 0. That makes sense. It's completely overfitting. It's the most overfitting you can be. Our test adversarial accuracy is 0.5, which also makes sense, but our privacy is low. Our privacy loss is high of 0.5. And then with a membership inference attack, 1.0, because you can easily differentiate between the training and the testing using the training data. And then using the discriminator testing, this is again that baseline of 0.013. And then finally, the utility, we use balance accuracy to measure that 48-hour mortality, and it achieved the best value, which makes sense again because it is the training data itself. But in terms of efficiency, it is not up to our specifications because we can't export the actual training data. Differential privacy obfuscation method, we can see that we get a little bit worse training adversarial accuracy, but because everything that's not a quasi-identifier was left as the original data, it's still overfitting to the original data. And basically, we see similar metrics to the original data throughout because all it was obfuscating was things like age, gender, and other quasi-identifiers. The overfit A&M is basically just a model, a version of a model that's going to be overfit to the original data. It also requires real data fed into it to generate data, so it's not really a candidate for being able to be exported from the secure environment. The fitted partisan windows method, we start to see a better privacy preserving method. So we see this 0.5 and 0.5 and 0.0. So we see that privacy loss that we want to see around 0. But with the partisan windows, you can actually still differentiate between the training and the testing data. So, and we can see that both in the membership inference, where we're getting a 0.81, as well as with the discriminator testing, where we're getting a value very close or at the same as the training data. but we do without even actually achieving that high of a balanced accuracy. And then finally, the two methods that are actually options, the Gaussian multivariate, which is because it only contains population level statistics, could be exported from the secure environment, and the HealthGAN, which can also be exported. And we're seeing mostly the same values throughout, except that we're just getting this better balanced accuracy, again, with the HealthGAN, not as good as the overfit methods as well as the original data, but we're getting good balanced accuracy that we're not seeing with the Gaussian multivariate. So now that we've tested our methods, now that we have ways to measure our performance of our methods, we're going to go into the optimal labs and actually replicate two different studies. So, so the first study that we're looking at, to kind of preface, these studies were performed on the real data in optimal labs by a colleague at RPI, and by Troy Vargas, and he worked with these two different data sets and wrote papers, published papers on the analysis from them. And so basically what we're trying to do is take the same data sets and replicate those studies with the synthetic data outside the environment. And so the first study looks at gastrointestinal symptoms and oral antibiotic use in children with autism spectrum disorder. And so basically it's trying to look at a population of patients with and without autism spectrum disorder and their number of GI diagnoses, as well as their number of antibiotic fills. And so we're looking at 3,253 patients with autism spectrum disorder and roughly 278,000 patients without autism spectrum disorder originally. This was sampled down to a 10-to-1 ratio to not overpower the autism spectrum disorder cohort. And then so we're looking at 11 different features, 5 demographic variables, and then 5 derived features, which are basically ASD, whether the patient is from which cohort they are in, early GI, whether they have a GI diagnosis in the early enrollment period, days stop, which is basically when they got a diagnosis, a GI diagnosis in the period which we were an autism spectrum disorder in this period here, and then how many early antibiotic fills and how many late antibiotic fills do they have, and then the outcome variable, whether there's late GI or not. So this is kind of I don't know, this is kind of confusing because basically this just has to do with how you do studies with medical data, but basically you need to follow patients through a period in time and ensure that you have what's called continuous enrollment, basically that you'll be able to track them through that entire time. And so in this early period, so basically they were tracking them for 5 years. So once a patient was diagnosed with autism spectrum disorder, they followed them for 5 years and monitored these values. And based off that 5-year period, you have an early enrollment period and a late enrollment period, and that's where these variables are derived from. And so their kind of outcomes were to look at the hazard ratios for the different values. And so specifically, one of the outcomes was looking at the hazard ratios for having 7 to 9 early enrollment fills of antibiotics. For the ASD cohort, the hazard ratio was 1.48, and for the population, it was 1.50. So basically, it was saying that they have a similar hazard ratio for having that many antibiotic fills, whether you have ASD or not. And so when we look at our synthetic data and how well that is performing, we can see over here in the ASD cohort, we have our demographics compared, the black being the real and the red being the synthetic. And we can see that we're matching pretty well across the high percentage classes. But again, this is a problem we have with the fact that GANs don't like to generate outlier data, because as the generator learns to generate data, the discriminator can easily, or it's easier for the discriminator to tell outlier data from real versus synthetic, because it's so guess, outlier. So basically the generator will learn to not generate those values as much because they don't fly under the radar, if you will. And so basically we can see here that these lower percentage classes are not matching as well. Now, in the total population, which is 10 times the number of data, we can actually see that they're matching a little bit better just because there's that much more data and therefore that many more people in the lower percentage groups. And so we can also use our nearest neighbor adversarial accuracy metrics to measure our resemblance. So we get for train and test, we get 0.52 in both, almost 0.53 in test, and therefore we have a good privacy loss and pretty good resemblance. We can also see with our membership inference area under the curve, we're getting a 0.5, which is exactly what we want to see. And then for discriminator testing, the test data as a benchmark is getting a distance of 0.008, and the synthetic is getting a distance of 0.02, which is indicating that we are not overfitting to the data. When we come down to utility, we're going to compare those Cox regression hazard ratios and their confidence intervals. And so when we look at the ASD cohort 7 to 9 fills, the real data was getting so we have a slightly different data set than the original paper, just because of the way accessing the data in OptimLab works. But basically, when we ran that analysis on the real data, we were getting a 1.25. And then when we ran it on the synthetic, we were getting a 1.49. And with the population, we're getting a 1.23 and a 1.25. So again, in the real column, we're seeing that same relationship that they saw in the study where they're about the same value. And in the synthetic, we're not seeing exactly the same value, but we're seeing the same effect, which is that both are saying that this is a that 7 to 9 fills is a hazard as a hazard towards late GI symptom or late GI diagnoses. Sorry, and so we can see here with the coefficients and their confidence intervals. Again, the black is the real and the red is the synthetic. We can see that we're getting overlapping in almost all except for late fill here in the ASD cohort, and overlapping in all of them in the population. And again, this is where the fact that the population is 10 times the data helps in terms of just being able to create synthetic data that looks more like the real data. In the second study, we basically take that same cohort of patients and kind of expand the study. They looked at basically, if you take that same autism cohort, can you cluster the cohort by their comorbid conditions? So if you take GI as one category of comorbid conditions and add on these other 6 categories, so we have 7 categories of comorbid conditions, can we cluster the ASD cohort based off of that? And so these categories are auditory disorders, developmental delays, gastrointestinal disorders, immune disorders, psychiatric disorders, seizure disorders, and sleep disorders. And so basically, this is measured every half year by number of diagnoses in these categories. And so this creates 70 features because we have 10 time points and 7 categories. So this is kind of where we get into quasi-longitudinal data, because we are recording that, or we are measuring over 5 years, but basically we still have 1 row equals 1 patient formulation that we want to see for the HealthGAN right now. In terms of this, just creates 70 different derived features for one patient, and then we have demographic variables as well that we can put in that same row. And so what they saw in the original study was they clustered into 3 different groups. They had a high, mid, and low cluster, and this was in terms of number of total comorbid conditions. And so on the high and the mid were about 25% of the group, and the low was 50% of the group. And so basically, they were seeing the low cluster was having a rough number. The number of comorbid conditions was about the same as the population, and the high and the mid were basically much higher than the average in the ASD cohort. So we'll see that in a bit. But going back to those PCA plots, we can use that same PCA plot structure to compare our real and our synthetic data, as well as how we're performing in terms of our clustering. And so right here we can see with the real data, when we take the two-component PCA, we can see that the low cluster here in green, the mid cluster in blue, and the high cluster in purple, we can see that they're roughly the same across the real and the synthetic data, which is what we want to see. And then in terms of our same nearest neighbor adversarial accuracy metrics, we can see roughly the same. We were getting a slightly worse resemblance than we were seeing in the previous data set, but we're still getting a good privacy loss. Membership inference is still at 0.5, which is good. And then the discriminator testing is closer to the test, but still showing that we're outside of test and therefore not overfitting by the discriminator. And so we can compare, now that we have this kind of quasi-longitudinal data, we can compare over time how well we're matching the original data. And so what we see here is so the top here is the real data, these two graphs, and the bottom is the synthetic data. And so the top here is looking at just that category of auditory disorders over time. And we can see that this high cluster in blue comes starts low, peaks high, and then starts to decrease. The mid cluster, as well as so the mid cluster is in gray and the low cluster is in red. And so we kind of see that kind of high, mid, low structure here. And in the population and the ASD are kind of in the middle as well. And we kind of see that same relationship in, although much rougher, in the synthetic data. Now, in the development disorders, this is kind of one of the interesting aspects of the clusters, is that while the high in general had the highest number of comorbid conditions, the mid cluster was the highest in just the developmental disorder category. And so we can actually see that in the real data here, where the gray, the mid is the highest, and we can see that in the synthetic data as well. And then if you kind of combine all these categories and just look over time, we see this again is the real over here, and this is the synthetic on the right. And we see that the high cluster starts high and then kind of crosses over the mid cluster. We see the overall ASD cohort in purple here in the middle, and then we see the low in the population almost at the same level down here. And we can see that roughly over here in the right. We're roughly getting those same trends. These are starting to match up, which they're not crossing over exactly how they are in the real data, but we're roughly getting the same trends, which is what we want to see in terms of utility while maintaining privacy. So now that we have models that are working, we want to export them from Optum Labs. And so basically they do their own statistical value evaluation, taking into account the metrics that we've devised and what we can tell them about the data, but they want to do their own independent analysis, which makes sense. And so basically using our data, our model, and our metrics, as well as their own methods, they evaluate the model, and then we already have one model that's exported, and they're working on evaluating a second model to get exported out of Optum Labs. And then in terms of conclusions, or I guess future work, we're trying to add longitudinal support for the HealthGAN. So we have that quasi-longitudinal that I was talking about at the end there, but we want to get more support for like real longitudinal data. We also want to be able to try and increase the computational efficiency of the HealthGAN. Right now, you do need GPUs to be really effective in terms of generating synthetic data with the GAN. We also are creating a Python package, which you can see on GitHub right now, and Karen has done a lot of work on that. And it is mostly, I think, doing all the functions of that we talked about today. And then, I mean, down the road, we want to be able to evaluate universal utility, as well as try other methods besides the HealthGAN and the Optum Labs environment. Frozen here? That is basic. Okay, yeah. I just wanted to thank everyone that I've worked with over my years here. But yeah, are there any questions?
A minor had a question about the sort of the screening that Optum Labs put in place for releasing the models, and he asked if if HIPAA experts are involved in that.
I think they have internal, their internal evaluation has to do with that, yes. So technically all of their data is already de-identified and I think allowed to be, I don't know if quite exported is the right word, but like their data has already had some evaluation to make sure it's HIPAA compliant. So it's basically those same people who are going to go and look at the data again. Basically, I think the reason they don't, yeah. So yes, I think that somebody is evaluating for that kind of concern.
Yeah, if I could build on that, because some people might not realize what the Optum Labs data warehouse is, but it's, what is it now? Is it up to about 200 million lives, Andrew, something like that? It's a combination of clinical
Yeah, that sounds about right.
Yeah, it's clinical data, what they call administrative data or records data, and some overlap, which they refer to as linked data, which is nothing like what we at RPI call linked data. And then the data in the Optum Labs data warehouse is double de-identified, which is reviewed by a HIPAA/privacy expert. So that's the basic context. It's a secure environment. All the computing that Andrew and anybody that works with Optum Labs data is done in a virtual desktop environment. No data under any circumstances gets, that's part of the Optum Labs data warehouse gets exported from the Optum Labs data warehouse. There is a limited ability to export results, obviously, because people publish from it, and that goes through a normal review process. So there's all of that context. Furthermore, the views that you are allowed to have as you go through a project review process, there's a limit to what you can, the limit to the different views, because there's always a potential for de-identification based on combining different views. Which is statistically difficult to do. They make it more difficult by limiting views, and also you're under agreement not to try. So this is sort of the context that we created this project. And so the review process that Andrew went through is a totally new thing that had to be created for us, for Andrew, because nobody had conceived of this until this synthetic data effort started off. And we're eternally thankful to, in particular, to people like Bill Crown, who's the chief scientist of Optum Labs, for shepherding us through this process so that we could have an export process and get the model on the outside. As Andrew said, one of the criteria is, as part of the model, you can have none of the original data. That was that bottom level criteria for, what did you call it, Andrew? The
efficiency?
Was it efficient? You basically, you can't, if the model requires you to have any of the original data, you can't do it.
Yeah, exactly.
So only those two leftmost ones even qualified. But anyways, that's kind of the big context for even getting the models out. And again, none of the synthetic data that was actually generated experimentally within Optum Labs environment was exported. The models were exported, and then synthetic data was generated on the outside, which is pretty novel. Okay, so any other questions? I'm trying to. Go ahead.
Here, go to. Have you considered applying this to non-EHR contexts? So, for example, social services.
Sorry,
things where there are like. Sorry, I can type my message in the chat.
Applications to non-medical contexts, is that what you were saying?
Or contexts where there's it's more qualitative types of data. So for example, coding or in social service evaluations or things like that, where you're generating, for example, text.
Okay, yeah. So, I mean, we definitely were trying to think about qualitative in terms of like categorical data, but we haven't done anything in terms of like text. I think that would be more of an application towards the longitudinal or time series data. I mean, just because a lot of text can be interpreted that way. I think that it would be hard to do text kind of as is, as like one feature or something like that, unless you were able to kind of personally evaluate that. Optum actually has a lot of access to handwritten notes, for instance, from doctors, which would be pretty hard to do. So it would be, I mean, it's kind of two aspects of that. It's pretty hard to create a synthetic version of that because there's so much identifying information in a way a specific doctor might write. So that could be an issue, but also just like getting valuable information out of that can be then generated by the GAN. So I think it would be a hard trade-off, but I mean, that would be an interesting area to try and work in.
I was just thinking, I've worked with some HIPAA protected data, which was sort of episodic service things with behavioral health services and so on, where you're not really, there's not a lot of numbers there. Particularly we're talking behavioral health. So it can be quite interesting. And you're right, the text, the doctor's descriptions, the case logs give things away. I would find it really interesting to have text like that.
Yeah, that and cost were one of the big areas that kind of steered us away from, because cost, again, can impart so much information about a specific location potentially, just because cost has like, there's so much precision to how much a specific procedure or something might cost. So yeah, I mean, I think that the difficulty there might not only, definitely in terms of text, be getting valuable information out, but generating it privately.
Have you looked at, there's, is the NHS in the UK doing work like this? Because I know they have some really fine-grained data, and actually a lot of problems come out of that because they have like really fine-grained postcodes, for example, but at the same time, it's quite interesting in terms of inferring environmental impacts and things like that.
Yeah, no, I actually haven't seen anything. I haven't looked into that really, though.
There's an organization called Cancer Research UK, which handles a lot of that data related to cancer. I might look into.
Okay. Yeah.
Are there any other questions? I had one question, and then we should wrap this up. So one of the things that's really interesting as part of the COVID-19 data collection and trying to deal with the pandemic is tracking of contact tracking, which would seem to be, for researchers, really interesting data to get a hold of, but it's, by its very nature, it's the opposite of privacy preserving. And so I'm wondering wondering how this approach or something like this approach could be applied to creating useful synthetic data for contact tracing data for researchers.
That's a good question. I think in terms of like, if you had actual like location information, I think it would be pretty hard, at least in like rural areas. So this is again where issues regarding generating data that's too specific in terms of geographic or cost or something like that, where the kind of like snap to grid is like much easier in the rural areas. So in a city, you could generate maybe some synthetic location data that wouldn't be that bad, but in rural areas, it'd be hard to generate believable synthetic data that's not reducing privacy. But if you can, I don't know, I guess my first attempt at that kind of a thing would be to translate the data into some feature-oriented things to get the location, the exact location information out of there. But I think once you did that, that could be interesting in terms of maybe looking at like relationships between like where people are and where people are coming into contact most frequently or something like that. Maybe, I don't know. Yeah.
So I hear what you're saying. For one comment on your answer, it's actually in the cities and dense populations that you need this the most. So it's kind of working in favor in that direction. The other thing that I think you're getting to at the end is getting sort of meta information about the precise locations, proximity, that sort of thing, rather than the absolute information. Maybe that's, if you could synthesize based on that, I think that's the point that you were trying to make. That could be useful.
Yeah, exactly. Like in terms of like where people are coming into contact by like in like specific and like you could use specific distances or something like that, as well as like generic locations. But yeah, I think that it would just be really hard to do it with specific locations and preserve privacy appropriately.
Okay. So are there any other questions? So let's all thank Andrew. All right, people came off mute. They actually do that. That's good. So once again, we will post a recording of this. It's well done, Andrew. It was almost as good as the first time with the earthquake.
Thanks.
A little bit less excitement. So we will post this via the IDEA website and the IDEA YouTube channel. And there is another webinar, the last of the COVID-19 term, next Wednesday. It will be Tetherless World graduate students doing their end of term lightning talks virtually. And that's the deal. So thank you very much again, Andrew, and thank you everybody for joining us.